this video, I'm going to demonstrate solving this resistor network, working it down using theory, series and parallel combinations to get it down to one resistor, and then answer the questions, again, still using theory of the specific resistors asked about, and then also simulate it. So I'm going to rebuild a circuit and simulate it straight off. DC power, ground. I need resistors. That's under basic resistor. I'm just going to grab 1, 2, 3, 4, 5, 6 resistors and then change their values. That might be a little easier. 2, 3, 4, 5, and 6. Okay. And then I didn't want a 7th one. Cut. Okay, so 1 was positioned. Undo. Let me grab the label. 1 was positioned here, and 2 and 3. Then 4, 5, and 6 are rotated. 5 happens to be over there. Not that the numbers really matter like that. And then this was a 6 volt. The R1 was 5.76. Was a 4.75. The 3 was a 3.83. The 4 was a 2.87. The 6 was a 5.11. And the 6 was a 5.11, and the 5 was a 0.27. The 1, not that it matters that much. Okay. And then figure out these connections. Okay. So there is the circuit, 6-volt battery, R1, 576, R2, 75, R3, 383, R4, 287, R6, 511, R5, 1.27. Okay, and then are asking for the voltage and current of the 287. So let's do at least the voltmeters. That's not what I want. I want indicators, a voltmeter. I want a voltmeter here. And then one for the 127. I'll make that a vertical. And then let me get the ammeter while I am here. And I'll get an ammeter. And what do I want to do? I want to stretch this out. So I grab those, stretch that out. And break this and put this ammeter in there between the resistor and there, and then the voltmeter in parallel. And then this voltmeter in parallel 7. And I want this ammeter like this, put the ammeter here, and make it look not very nice, but there we go. Okay, run the circuit. And so now I know the answers I'm expecting. So here we go. I don't need to keep that in the whole time. Okay, so now we've built the circuit, we've simulated the circuit. So now we know what answers we're going to get. So let's go get them in theory. Okay, so we look at this circuit, we're looking for series and parallel, and we can see that 2 and 3 are a series combination. The current will come out of the 6, come to this point and break, but whatever goes through the 2 must go through the 3. That means 2 and 3 are in series. And then all that current gets back together, and all the current that came out of the battery goes through R4, and then it splits up again, and then some of it goes through R6, some of it goes through R5, and then it gets back together. But R6 and 5 are in parallel. There's a wire connection on one side, there's a wire connection on the other side. And so those are the 2-3 series combination, and the 5-6 parallel combination are, you know, far away, not touching each other. It's sort of easy for me to do both of those replacements simultaneously. I don't have to do them simultaneously, but I can. I'm going to say R2 and R3 in series. I'm going to say R5 and R6 in parallel. And then let me bring up my calculator. Here we go. So in resistors in series, simply add. So I'm going to do 4.75 plus 3.83, and that is 8.58, and the 5 and 6 in parallel, that is 5.111 on plus 1.271 on equals, perform the addition, and then the final reciprocal. So that's giving me a 1017, I'm going to say 1.017. Then I would like to make those replacements. If I were not recording, then I would probably do this on a piece of paper, but I'm going to do this in my simulation for the sake of the recording, then this can all be recorded. So I've made my space bigger. And I'm going to copy my circuit. And then paste it below. And I'm going to make my replacements. I'm going to get rid of 9. And then make the replacement, what did I say? 8.58. One of my replacements. And then I made a replacement of what? The parallel combination. So I'm going to get rid of all of this. And say what? That the 5-6 combination was replaced by this. Now I called it 12, and the equivalent value should be 1.017. Okay. And let me turn on the simulation. And this is one advantage of doing it. This is more tedious than it would be just on a piece of paper, but one advantage is I can see that I haven't affected this current. Okay. So now what comes next in here, I can see that what was originally R1 and the R2-3 combination, those are in parallel. So I'm going to say R1 and I'm going to call it R2-3 are in parallel. And that's going to get me, that is this 576 and this 8 right there is a parallel. Let me see if the scientific holds a little more information, or if I make the calculator bigger, does it hold more information? So it's a 5.76 1 on plus 8.58 equals, to do the addition, 1 on 3.446. Okay, so this, I'll do another replacement and replace that by 3.446. I can do these if I want. The 2.87 and the 1.107 are in series. I'm just going to wait because then I will have 3 things in series next, and that will be just as easy. So let me copy this. Let's paste it down here. I'm getting rid of this guy, replacing this value with, what did I say? I think it was 3.446. I ruined anything yet? I'm getting the same current, the same voltage for the 2.87. That's good. And so now what do I have? I have the thing that came from R123 and R4 and R56, I'll call it. They are in series, so that's just an addition. And so is that the 3.446 plus the 2.87 plus the 1.017. And that is giving me 7,333. Okay, so I'm going to try one more replacement, copy all this. There we go, copy. Paste that guy in there. I'm going to delete this one, because that's the one that has the voltmeter and the ammeter, so that's useful to me. I'm going to delete this one, remake the circuit, change this guy to my voltmeter up a little bit, change this guy to what did I think it was? 7,333. Is it the same? It's no longer the same resistor, so I can't expect the voltage to be the same, so I shouldn't even have kept the voltmeter. So I'm going to delete that. But the current is the same current that I expect to be right. Okay. So now that's my overall current. Now let's do the theory, to get that current I've been seeing all along, V equals I times R. And so the current is going to be V over R. So much easier if I'm just writing it on a piece of paper, but for the recording, so it's 6 volts divided by my 7.333, and that's equal to 6 divided by 7.333, and there is my 0.818 milliamps. So I found the equivalent resistance. That's usually something I need to answer in these kind of problems. And then I have, through my theory, I have found the overall current. Now, that's the overall current through this one resistor. But if I go back a step, I had 3 resistors in series, and resistors in series have the same current, and they have the same current as their equivalent. And so I can say that the 2.87 sees this 0.818. And let me put in milliamp for a unit here and V for a unit of my volts. Now that I know through theory that this was the current of the 2.87, I can get the voltage. Again, a resistor obeys Ohm's law. So I can say that I know the 818 was the current in the resistor, and the resistance is the 2.87. And so I can find the voltage. I've been simulating it all along, but now let me get it in theory. 0.818 times 2.87. And that is this 2.3. And that's a volt. So that was here. So we see that both simulationally and theoretically now. And now we want to go after the 1.27, and we want to go after that sort of theoretically with equations. So I'm going to take another backward step. That's uninteresting in terms, that backward step is uninteresting in terms of the 1.27. So what I'm going to do is find what's the voltage here. I found the voltage for the 287. Let me find the voltage that will be useful. Let me find this voltage of that equivalent resistor at some point. So I can also find Ohm's law at this stage, and this 818 milliamps was going through this 1.107. So what would be there? And that would be 0.818 times 1.017, and that would be 832, I'll call it. And that's a voltage. So that's the voltage seen by this 1.17, and that is the voltage seen by these two in parallel. We want to take the backward step. This 1.17 came from the 511 and the 1.27 in parallel. Things in parallel see the same voltage and see the same voltage as their equivalent. So we calculated in theory this voltage of the 1.017, and so we know that that is the voltage of the 1.27. So we have this voltage here theoretically 0.832. I'm also seeing it simulationally, so that's a good check. And then I can do an Ohm's law, not on the 1.107, but on this 1.27. They're all resistors. They all obey Ohm's law. We know what? We know the voltage is 0.832, and that is equal to the resistance of 1.27, and then that is times a current, and solve for that current. So the current will be 0.832 divided by 1.27. Writing it out in tedious detail. Okay. Clear. 0.832 divided by 1.27. And I'm getting 0.655 milliamp. And I compare simulation, 655 milliamp in the simulation. Okay. So that's what I wanted to show you. I had this series and this resistor network where they're using series and parallel equivalent resistance combinations. I can work it down to one resistor, and then I can apply Ohm's law to find the current. I know the voltage of the battery. And so I worked down. R2 and R3 were in series. R5 and 6 were in parallel. So that got me from this first circuit you see at the top to the next one down. And then this now labeled 7 and 8, they were in parallel. So we placed them with this 9, and then the 9, 10, or whatever value that is there. 13, the 9, 13, and 14. They were in series, so we got down to 1. Then a simple Ohm's law calculation got this current. And then we can start our, what I refer to as the backward steps. So if I take one backward step, this 7333, where these 3 in series, things in series have the same current. So I can use this current I found both simulationally and theoretically, and find this voltage up here. So that was one of the questions I had asked. So I had one of the questions I asked both simulationally and theoretically. I never did put in the 655 here. And then I take another, well, I can find this voltage. I can also find this voltage. So I found the voltage of the 1.107. And I can, it's the same here as it was here. And then finally this 1.1017 came from these two in parallel. Things in parallel have the same voltage and the same voltage as their equivalent. So I knew this voltage, that was the 0.832. And from that, then I could find the current, and that answered all of the questions that were asked. We did everything in theory. We did everything in simulation. So we've done it both ways and have checks. And that's what I wanted to show you. So thanks for your attention.